Hi all and welcome to this tutorial on how to forecast and predict snow. I'm Carl from the Irish Weather Network and I will try and simplify why it is hard to forecast snow at times, the types of snow and the elements that we need for all of it just to come together. This is a lengthy but informative tutorial, so let's talk about one of my favourite weather types. Love it or hate it, snow can be magical. It can change the scenery, freshen up the air, make it feel crisp, and it's fun. But on the downside, it can cut off communities. You could be stranded if caught outside and shut down local economies if the infrastructure is not in place. From a weather point of view, it can be tough to forecast it. This tutorial will focus on how to predict snowfall and what elements are needed in order for snow just to occur. In places like, say, the US, Canada, Scandinavia, Russia, and other parts of, say, Asia, snow is a regular occurrence in these regions, and the elements are easily in place for snow to settle throughout the entire winter period. In other parts of the Northern Hemisphere, like the Pacific coastlines, North Atlantic regions like Iceland, Ireland, UK, and parts of Central and Western Europe, there needs to be more ingredients involved for snow just to fall, let alone to settle. I hope to cover this in its entirety here and make things slightly clearer. If you have any comments, please do put them in the comment section below and I will get back to you. I will go through each element involved, set up a synoptic, starting off with, say, temperature, the dew point temperature, location, sea level and altitude, moisture, air mass, convective snow, thundersnow, frontal snow, types of snow, blizzards, drifting snow, and snow clouds. So we will focus on, say, temperature first. We measure the air temperature approx 4 feet off the ground, over short grass and away from any concrete structures to get a true representation of air temperature. Surface temperatures are different again, and I will do a separate video on both. Air temperature, well, this plays a critical role in forecasting snow for obvious reasons. The colder it is, the more likely we could see snow occurring. We want the temperature to be below 4 degrees for the snow to have a chance of occurring, but we want to have temperatures of 1 degree Celsius below to have snow settling on the ground for any great length of time. Now, as the surface temperatures coming out of autumn into winter can still contain some residual heat, the most favourable months are typically here in the Northern Hemisphere is January and February, that mostly have the colder surface conditions as the sun's tilted away from the air in the winter months, so less of the sun's heat reaches the surface. There are exceptions though. Large continental land masses and unique cold events, snow can settle early on in the winter season. Another important element for snow to fall is the dew point temperature. Dew points are an important element used for predicting snow, but also used to forecast fog and thunderstorms. I will do a separate video on explaining what dew point temperature is, as it can be complex, but it's the temperature at which the air needs to be cooled to be saturated. But back to snow and how a dew point temperature can predict and plays a vital part of the formation of snow. We want the dew point temperature to be below 0 degrees Celsius in order for snow to fall to the surface in its solid state. Rain starts out as snow in all cases. As it falls through the atmosphere to the surface, it heats up and melts, and depending on the air temperature in the atmosphere, it can be ice pellets, sleet, wet snow, and there is a difference between them all. And dew point temperature plays its role. For example, if the air temperature is, say, 4 degrees Celsius and the dew point is 2 degrees Celsius, rain will occur. But if the air temperature is 4 degrees Celsius and dew point temperature is 0 degrees Celsius, snow can occur. If the air temperature is 1 degree Celsius and the dew point is 1 degree Celsius, as it's very cold at the surface, snow will fall, but it'll be wet snow. If the air temperature is 1 degree Celsius and the dew point is -1, then snow will be more powdery. So the lower the dew point temperature, the more powdery the snow will be, as it's not holding as much moisture. But as I will explain later on in this tutorial, why did it rain when the air temperature was -4 degrees Celsius and not snow? Yes, -4. I'll explain that later on in the Airmass section. Another example, I recorded my air temperature of 2.6 degrees recently, and dew point was 2 degrees, and it was raining. A little hint of some sleet, but the majority was rain. So it can be a fine line with air temp and dew point temp to determine the type of snow or whether snow will fall even at all. Now, another important element is your location. We'll focus on sea level here. So, the location is important too, either landlocked or living by the coast. Sea or ocean retain heat more than the land, and temperatures fluctuate very slightly throughout the year, only losing heat gradually and therefore only heating gradually during the summer months. This depends on latitude, but let's keep focused about not talking about equatorial sea temps as it doesn't snow there. But back to more northern temperate latitudes like here. Let's take, for an example, we are expecting snow showers in the forecast. Peter lives on the windward coast and Paul lives 50 kilometres inland. Peter only gets sleety rain by the coast while Paul is getting snow that is settling inland. Why is this? As the air moves over the warmer sea, it transports heat and modifies the air above it, raises the air temperature and dew point temperature even slightly so that both melting points are above freezing. But as you go further inland, the modified air off the sea loses its heat and the colder land now beneath modifies the air colder, dries the air out, and the dew point and air temp are perfect for snow to fall to the surface. But Peter and Paul's other friend Patrick is even further inland, say 100 kilometres from the coast, and gets no precipitation, but he was in direct line of this shower. Why? As a shower moves over the land is colder and therefore the air above it is drier. So the atmosphere loses its moisture content and dries out. So the air can be too dry to hold moisture due to how cold it was much further inland. But if you have more of a gale force, say wind blowing the shower along, well, this shower may then hit Patrick 100 kilometres inland from the coast, and he may get some snow, so the wind is just another factor. Location, altitude, say, probably by far the easiest to get snow. If the air temperatures predicted to be at sea level are to be low, because air temperatures drop by 1 degree Celsius for every 150 metres in altitude. For example, the Empire State Building in New York is 453 metres tall, so that means it's 3 degrees colder at the top than on the street level below, and it has rained at street level while snow on the viewing platform. So any hilly and mountainous areas will stand a higher chance of snowfall. But why does it snow more in hilly and mountainous areas? This is a process called orographic lift, whereby on the windward side of the mountain, the air is forced to rise and enhancing snowfall intensity by rapidly cooling condensing air droplets into forming more and more snow. Sort of like a conveyor belt. This tends to occur in frontal snowfall, but mountains do and have create their own microclimates as well. Now, another important element is moisture. Well, the moisture has to be present in order to condense into a cloud for it to snow, but it can be too cold for it to snow. Well, when dew points are concerned, that is, the air can be too dry for it to snow. So if it's very cold, and I'm talking about below minus 20 degrees Celsius or minus 4 degrees Fahrenheit, the air can be too cold and dry to hold moisture. The colder it gets, the less likely for it to snow. For example, more snow falls in Scotland than it does in the Arctic. Whiteout conditions at the poles is caused when the snow is whipped up by winds to make blizzard-like conditions. Now this brings us on to air mass. Air mass plays a part in snowfall. In the northern latitudes in the northern hemisphere, we associate winds from a northerly direction to bring us snow, and for obvious reasons. These winds come from the North Pole or Arctic region, but snow can come from any direction, even from the south. It's all to do with the type of air mass that's in situ already. For instance, a cold air mass resides overhead for a period of time, and the surface and air temperatures are low. Air is cold and other factors are in play for snow to occur. So the wind picks up from a south or southwest direction, and if you live on an island in the North Atlantic Ocean, be it Ireland, Iceland and the UK, we get snow falling widely from a typically mild direction. This is a returning polar maritime air mass, which means the cold air plunging down from the north around the low pressure has not got time to pick up the heat, but picks up a lot of moisture and drops a lot of snow. We can also have continental polar maritime air mass, but winds coming off a cold continent tend to be drier. Basically, you can receive snow from any wind direction if the elements are in place. Now, I touched on this earlier in the dew point section. How can it rain at minus 4 degrees Celsius and not snow? This air mass above us is very cold. Sub-zero air temperatures and ground temperatures even lower. It clouds up quickly from southwest direction with a warm front moving into the area. As cold air is much heavier and denser than the warm air rides up over the top of the cold air and tries to push it out of place. So you can actually have sub-zero air temperatures at 4 feet high, but in the warmer layer above, even at 300 meters up, the air can be several degrees above the freezing point. So the rain that is falling falls through a layer of very cold air and does not have time to solidify into snow and is super cold. And as it hits the surface of everything, it instantly freezes. This is called freezing rain. Probably more destructive than snow, as the weight of freezing rain can accumulate and bring down trees and power lines. This can happen over the largest of continents where temperature differences are more extreme than islands. But islands can receive a period of freezing rain in winter, just not as extreme as, say, in the US. Now we have convective snow, more common around island regions and coastal areas in winter. In summer, the convective showers occur over land. As the land is warmer and convection begins, storms can break out. But why convective showers occur only around the coast and not build over land in winter? Again, it's all to do with temperature difference. The sea temperatures are higher in winter than the land, but when you have a cold, cold air mass blowing over the warm sea surface temperatures, it destabilizes the air and convection can begin. So the heaviest of the showers occur at the windward coasts and can drift inland a bit, but lose intensity as explained in the Dewpoint section above. Convective showers don't occur over large land masses in winter like Europe or Russia, Asia, or mostly the US, bar one exception in the US, I should say. Two of the snowy cities in the continental US is Buffalo City and Syracuse in upstate New York, and are far from the ocean. They reside beside the Great Lakes of Ontario and Erie. Not only did these cities receive frontal snowfall, but convective snow in the form of lake effect snow, which works in the same way as showers building over the sea. But these large freshwater lakes can hold more moisture and push in over regions where the dominant wind direction is blowing in what we call shower trains and dump feet and feet of snow in a very short period. Now, thundersnow is a fantastic phenomenon. It's rare, but when it occurs, it's magical. Lightning is a bluish colour due to the light interacting with the snow, and snow can muffle the sound of thunder. It's actually a spectacular sight when it occurs, and mostly around coasts in the winter months. We'll talk about frontal snow now. Like showers, as with the nature of showers, they can be hit and miss. Snow can fall down in the next street and you could be drying in the clear. But with frontal snowfall, more areas are at risk from several hours of persistent snow. There are several forms of frontal snow, but we will talk about the main ones, which are a warm and cold front. We can have a clouded and a triple point, but that's for another day. Snow from a warm front would be more persistent form of snow, as snow can fall in advance of the front, several hundred miles from the passage of the front, so you can have a period of several hours of snow accumulating. And if that front stalls and comes up, say, against a blocking high pressure system, it can be very disruptive. As with warm fronts, these move slower, and the trailing front, cold front I should say, can catch up and form an occlusion. So cold fronts or troughs can bring a short period of intense snowfall, and these are more frequent across the North Atlantic, with places like Ireland, UK and Scotland, Iceland, the Faroe Islands can experience quite intense snowfall. Troughs can merge or organise into different bands, follow each other and form polar lows. Now, polar lows are more common in the North Atlantic Ocean, when wind conditions prevail over the North Atlantic coming from a northwest direction from Greenland. The interaction with Iceland forms these small lows to the lee of Iceland. They can travel to Norway, which tend to be a regular occurrence, or straight to Scotland and Ireland, which is a bit more rare. They are known as comet clouds. As the visible satellite, they resemble a comet, like a comet on your keyboard. A period of heavy snowfall within a cold core around a small low pressure system brings widespread snowfall, and these are rare events as conditions have to be ideal. Now, the types of snow. No two snowflakes are actually the same. With the amount of snow that can fall from the sky, each crystallizes in different ways. Some can grow large by attaching to other flakes, and some can be small. Now, snowflakes have a unique shape, and under a microscope you can actually see thousands of different patterns. The largest flakes fall in still and calm conditions, as the wind can't break them apart as they drift slowly to earth, while the smallest flakes occur in blizzards, as they don't have time to bind due to the strong winds and can feel like ice pellets in your face if you're lucky to be caught out in one. Now, snow pellets are super cool snow that can fall and melt, refreezes, and can bounce when they hit the earth. Snow grains, again, are smaller and softer in nature and generally fall from stratiform clouds. We talk about blizzards next. And these snowstorms, or whiteouts as they are called in some countries, are the same thing. Visibility is practically zero. Gale force winds and heavy snow is driven about in blizzards. They can pile snow up in areas quickly, called drifting, and whip up more snow from the surface and dump it somewhere else. Best to avoid driving and to stay at home if you're caught out in one of them. Stay off the roads and seek shelter, and hopefully you have the necessary equipment in your car or your vehicle that you're driving. Now, drifting snow. Well, as I touched on already in blizzards, it's caused when winds are strong, like in the blizzards, but winds don't have to be gale force for snow to drift. All it takes is some sort of strong wind and a lot of snow for drifting. The prevailing wind can drift snow up to the side of your house and car, making it impossible to access, while on the lee side of your house can be accessible, if sheltered enough, that is. With snow drifting up against your front door, it can make getting out of your house tricky. Drifting snow is what cuts off communities all over the world. If it's bad enough just to keep roads clear, it's not always practical to do so during a blizzard, but drifting snow can actually cut off communities for days. We talk about the types of, say, snow cloud. Well, there's no such thing as a snow cloud. Snow can just about fall from any cloud under the right conditions, but most of the time it's cumulonimbus, cumulus congestus, and nimbostratus. Now, cumulonimbus, this is the king of clouds, the deep convective beast that delivers the heaviest of snowfall to coastal regions in winter, thunderstorms during the summer. Snowfall rates are at the highest from these clouds, but they can form in trough lines as well, and they can be a period of heavy snow in a short amount of time. Cumulus congestus are a step below the towering cumulonimbus. These are common in, say, shower trains. If you're caught in the path of these, you can have continuous heavy snow for hours. Typically only a narrow corridor of snow, as a mile down the road it could be dry, and the shower train could be only a couple of miles across, but several miles long moving inland, just like in the case of the cities of Buffalo and Syracuse, which I touched on earlier with these shower trains. Nimbostratus is associated with frontal snowfall conditions, moderate heavy snow for hours over a wider area. You can also get snow grains from stratiform clouds like the stratus. Now, I just want to get a little bit more into technical detail. I want to try to keep this as simple as possible and so everybody can follow. But this warrants its own video, separate video, which I will do. But I'll touch on it for a second. We'll talk about upper air temperatures at, say, the 850 millibar level and the 500 to 1000 millibar geopotential heights of dam thickness are also used in the forecast of snow, especially temperatures at the 850 millibar level, whereas it gives a good representation of air temperatures at near the sea level, while dam thickness like the 540 dam line is usually a good representation of the transition from rain to snow. The shallower the dam thickness, the more likely the snow. Example, the 528 dam line or the 520 dam line, etc. Right, I'm happy to say it's over. We're finished. The tutorial is done. Thank God, you're probably saying now. If you stuck around this long, fair play to you. There is a lot to digest in this when you talk about the formation of snow and how to forecast snow, because sometimes it can be impossible no matter where you live. But like it is, hopefully I made it a little bit more clearer to follow and to understand the different regions and areas that can affect how snow can fall and settle. So look, if you like this tutorial, give me the thumbs up and hit the subscribe button and help me make more content like this and grow this channel further, because it's something I enjoy doing, and the knowledge that I have possessed over the 40 years that I'm studying meteorology, hopefully I can make things a little bit more clear for yourselves going forward. So like, until the next tutorial, hopefully it won't be as long. Hope you're still awake. Okay, thanks and take care of yourself. Bye bye.